So now we hopefully understand what a vector is and ways we can manipulate a vector. Let's now talk about vector sums. Let's say that I find a treasure map. Okay, let's say that you find a treasure map and it tells you this. Go 3 miles east, then at the big rock, go 4 miles north, then when you hit the river, go 7 miles, 30 degrees north of east. Okay, so where's the treasure? Well, how are you going to do this? You're actually going to follow the map, right? You're going to say, ooh, well, this isn't a treasure map. I guess this is a description of where the treasure is. So we're going to start. I guess it had to tell you where to start. Whatever. We'll just assume we know where to start. We're going 3 miles east, right? So let's just draw this to scale, right? 3 miles east. 4 miles north. So the 4 better be about a third as long as the 3. So 4 miles north. And then 7 miles, 30 degrees north of east. So I want to know how to go 30 degrees north of east. Let's put a coordinate axis. Let's measure up 30 degrees. Okay. And then make a vector which is 7 miles. Whoops. A vector which is, I guess I could have used those arrows. I forgot about the arrows. But anyway, a vector which is 7 miles long. And we can use a ruler to get the scale, right? So this is 7 miles long. And where's the treasure? X marks the spot. And there's the treasure. But where is the treasure compared to where I started? Right? What we've done is we have actually taken 3 vectors and we've added them up, right? By putting them head to tail. That's how you add vectors. You put them head to tail. We had 3 displacement vectors, and to figure out where we were going, we had to add them, right? We had to do one, and then we had to do the second one from the end of the first one, and then we had to do the third one from the end of the second one. So how do you add vectors? Whoops. You add vectors by putting them head to tail. And then the resultant vector, the sum, right? Where is the treasure? We've got to start where we started and finish where we finished, right? So the sum is right here. That's the sum right there. That's the sum vector. That's the sum of those 3 individual vectors. We could have, instead of following those 3 vectors, we could have just followed that purple line and walked straight, except that we might have gotten eaten by alligators or stopped by pirates or something. So, but anyway, the sum of the 3 individual vectors is the purple vector, the resultant. The resultant goes from the tail of the first to the head of the last. So we could just draw a scale diagram, right? Somebody gives us this treasure description of where the treasure is. We could draw a scale diagram and we could figure out how far we have to go. We can put on our armor so that nobody can attack us, and we can just take that straight line, take the quickest path there. We can do that by measuring the length of the purple vector. We could just draw a scale diagram, 3 miles, 4 miles, 7 miles, draw a vector that goes from the start of the 3 to the end of the 7, and then measure that length. And then take a protractor, put down a coordinate axis, and measure the angle of that vector, right? Angle, in order to find the net distance and angle that we have to go on. Okay, that's how to do geometrical vector sums. Okay, that last example made me think of something. Northeast is not a direction. It is not a direction. Half of you will use it at some point. It does not denote an exact direction. Northeast is a quadrant, right? So if you've got your compass rose and you've got east, north, west, and south, northeast is anywhere in here, right? So that is not a direction. It's not a vector direction. You can't use northeast as a vector direction. It also doesn't indicate whether you're going north of east or east of north, right? Because 30 degrees north of east is a direction. Because we can just take our compass and measure up 30 degrees north of the east direction, right? I'm going north of the east direction. And so that gives me 30 degrees north of east. That is a direction. I can go any angle. I just chose 60. I can go 60 degrees east of north, right? Start at north and go eastward of it. 60 degrees east of north actually gives me the same direction as 30 degrees north of east. I didn't mean to really pick the same directions. But anyway, so those are directions. But saying 30 degrees northeast, I don't know what that means. Is 30 degrees northeast 30 degrees north of east? Is it east of north? Or is it 30 degrees from the 45 bisector? I don't know what 30 degrees northeast is. I don't know what northeast is. It's anywhere in that quadrant. So you always have to use words like, and you always have to use an angle and a direction, right? North of east, clockwise from plus x. You got to give a direction from an axis. I should have said that. You always need to give an angle and a direction from an axis. An angle and a direction from an axis. So, 25 degrees clockwise from plus x. And 25 degrees clockwise from plus x. That's this here. So a angle, a direction from an axis. You might say, well, can't I just say north? Well, yes, that's a special case, right? A vector that points north. Can I say west? Yes. A vector that points west. Whoops, that wasn't quite west, etc. So I could say, my displacement is 3 miles north. That's the purple vector, right? D. There, 3 miles north. Okay, so that is a special case which north indicates it's 0 degrees along the north axis. Okay, let's come back to vector sums. So, one thing to notice is that vector addition is commutative. Okay, what do I mean by that? Well, let me redraw this on a new page. We had 3 vectors. We had our 3 vectors, which I'll just call A, B, and C, right? We'll just make them very general. They could be displacement vectors. We could call them D1, D2, and D3. They could be velocity vectors. We'll call them V1, V2, and V3. Force vectors, F1, F2, F3. Doesn't matter. But I'm just going to call them A, B, and C. The sum of A plus B plus C is the resultant vector that starts from the tail of the first to the head of the last. That's what we've done so far. Let's just call the resultant vector in this case, we'll just call it R for resultant. So the notation goes like this. A plus B plus C equals R. Okay. But now, also, so the mathematical property of vector addition is that vectors are commutative. I won't bother putting a title on the page. A plus B, equals B plus A. A plus C equals C plus A. So it doesn't matter what order you add them in, right? That means that the resultant vector is also B plus C plus A. So I could have gone first 4 miles north, then 7 miles 30 degrees north of east, then 3 miles east, and I still would have gotten to the same place. Vector addition is commutative. That is important because sometimes you're asked for a sum A plus B plus C, but it's much easier for some reason to write them in a different order. As long as they're head to tail, doesn't matter which order you put them in, the sum is still going to be the same, as long as they're head to tail. So I talked about doing the sum with a scale diagram. You can just measure these things on a paper with a compass and a ruler. You can do that. But we have analytical ways of adding vectors. We have ways.